Okay, so as promised, let's continue Tuesday's lecture. Here's an example of a moment of inertia for composite areas, and this is something similar to what you will have on the final. Okay, so let's go ahead and refresh our memory. This is the table from your textbook, chapter 9, and notice I added a couple more moment of inertia information on the right. First is the moment of inertia of the semicircle when you're rotating about the centroid, and the centroid is located right here. In this case, we're rotating about the axis that is parallel to its diameter. And the second one is the moment of inertia rotating about its centroid. Again, the centroid now is located here, as you can see, and we're again rotating about the axis as parallel to its radius, either the vertical or the horizontal radius. These two results are simply using deployment of the parallel axis theorem. So let's go ahead and refresh our memory. What exactly is a parallel axis theorem? The parallel axis theorem is the way that we can derive our new moment of inertia about x. Actually, I probably shouldn't have tried. By adding the moment of inertia about its centroid, and the dig is distance located from centroid to axis of rotation. So this is a way that we can identify our moment of inertia rotating anywhere. Let's go ahead and take a look at an example and then see how you can use the centroid, or actually the parallel axis theorem. So the first step I'm going to do is determine okay, so let's say that's a part of the problem. And how many different shapes am I looking at? Of course, you can look at it from many different perspectives. But I am going to look at it as, let's see which way is easier. Okay. My area 1 is this triangle hole right here. Area 2 is this big rectangle. Actually, I don't think that works, so let's try something. In this case, it may be easier if my area 1 is this piece, area 2 is this piece, and area 3 is just the quarter circle. So here's my 1, here's my 2, and here's my 3. So let's say I'm interested in finding my centroid x and y. The first, is there any axis of symmetry? In this case, we don't have any axis of symmetry, so we have to proceed to the next step. Set up a table. And this is the table that I need to set up. My shape, area, x bar, y bar, x bar, a, y bar, a. So here is my shape 1, shape 2, let's go a little bit longer. Shape 3 is my quarter circle, and the last one is my row. My x is x bar of each piece, and my y bar is summation of y bar of each piece. Okay, so here we go. Let's go ahead and figure out what are the areas of each piece. The area of each piece, this is here, here, and here. These two distances are 1/3 of the height from its base. These two distances are 1/3 of the height from its base. And where can you get that information? You can get it from chapter 5. Remember that table that we have for some common areas? And this distance is 4r over 3 pi. Okay, so let's go ahead and plug it in. Let's get the areas A first. So this is 4 times 4 divided by 2. And the same thing with that one. So here my x bar, let's go ahead and assume that's my x and the y axis that I want to take my centroids about. Remember, that's my origin O, right? Therefore, for area 1, the triangle on the left, x is in the negative axis. Therefore, we need to figure out what that is on the left. And remember, the distance is 1/3 the height. The height is 4 inches, so minus 4/3. The y-axis is positive. Again, 4 inches in the height, so it's positive 1/3. And x bar times a is then minus 32 over 8. And this is 32 over 8. Okay? Oh, sorry, not 8, 3, right? Next, number 2. In this case, my x is going to be positive, so it's positive 4/3. However, my y is going to be negative since my centroid here is below in the negative y-axis, so I have minus 4/3 over here. And the same thing, except that I am now reversed. Okay. And here's my quarter circle. The area A of a circle is pi r squared, but since this is a quarter circle, so it's 4 pi. Oops. My x bar for the quarter circle is 4 times 4 divided by 3 pi. My y bar, same thing, 4 times 4 over 3 pi. And I can then multiply x bar multiplied by a. I'm going to have the pi and the top and the bottom will cancel each other out. So we're going to have 4 pi 16 over 3 pi. 64 over 3. Same thing. Yes, this one. That's going to be 64 over 3. So all I need to do is add my areas up. That's 16 plus 4 pi. And x bar. Add them all up. Actually, we don't need to do this one. We don't need to do this one. These two will cancel each other. I also have 64 over 3. Y bar, these two will cancel each other. I have 64 over 3. Therefore, my x bar is 64 over 3 divided by 16 plus 4 pi. And my y bar is 64 over 3. And that's also 16 plus 4 pi. You can go ahead and hit the calculation and you can get a number here. Okay? So this is how you get the centroid. Let's now, I'm going to use this. So where would the finalized centroid be? Probably somewhere here. Okay? We can quickly punch in the calculator and see what kind of number do we get. So 64 divided by 3 divided by 16 plus 4 times about 0.75 inches. Okay. Okay. Next question. So let's pause here for a minute. Next question. Let's go ahead and talk about how do we find its moment of inertia. Let's say I want to find its moment of inertia rotation about the x-axis. Okay. How do we do that? Well, there are three pieces. We know the Ixx is going to equal to the Ixx of this piece plus the Ixx of these piece plus Ixx of these piece, right? We say they're added together. But what are the Ixx of the triangle? Okay, and this is where you can go to the table that we had prior to find Ixx of the triangle. So this is your of the triangle. Okay, let's go back to the prior table and see. So axis of the triangle, if you go ahead and look at it carefully, we're rotating about the x-axis. Notice we're x, not x prime, right? So this is what we're looking for. Ix is 112 bh2. Okay, 112 bh2. So 112, my base and then my height in this case are the same. So is 64 over 12 for and that's inches to the fourth. Let's go ahead and look at Ixx of this particular triangle. It's triangle again, so it's the same thing. It's 112 4 to the cube. So it's 16 over 3 inches to the fourth power. Oops. How about Ixx of this piece? Well, again, go back to what we had. We say is equal to right here 1/16 pi r to the fourth. So my Ixx of this piece is going to equal to 4 pi plus 216 or 16 over 3. That's my final answer. Okay, easy enough, right? Okay, let's now say I'm interested in finding my rotation about the moment of inertia. So here's my moment of inertia of this entire piece, or we can call it x prime. How would you do that? Well, according to the parallel axis theorem, my Ixx is equal to this distance d plus x prime, right? Or this is equivalent. Some other book will use I bar x. This simply means that this is moment of inertia rotating about centroid. So as you can see, whenever you're trying to find the moment of inertia around different axes, you need to use a parallel axis theorem. Since what we found here is the rotation about the x-x axis, which is that one, right? And now we want to find the moment of inertia on a different axis. You see, you don't have to redo this whole thing again. All you need to do is apply the parallel axis theorem. So my parallel axis simply state that my ixx is d squared plus a plus that. But what is my distance d? The distance d is the distance between the centroid and my axis of rotation, right? And I know what this number is, so I just found this. So this is 32nd divided by 3 plus 4 pi. And that is equal to my distance d. So what's my distance d? Well, we found it in the prior slide. It's about 7.5. And my total area, I also found in the prior slide, right? As well. So you can see, I cannot go backwards, find the moment of inertia. Centroid. Going backwards. Okay? Hopefully does that make sense? Okay? So, that's it then.